Hi everyone, I would like to invite you to the journey through the portable switch architecture implementation for eBPF. In this tutorial, together with Mateusz and Jan from Orange, we will present a deep dive into design and implementation, as well as the Getting Started guide. The agenda of the tutorial is as follows. Firstly, we will show the overview of the PSA eBPF. Next, I will present a necessary background on the eBPF technology and a short overview of portable switch architecture. In the next section, we'll go through the design and implementation of PSA for eBPF. In particular, I will focus on how the PSA is mapped to the eBPF subsystem and how different P4 objects such as PSA extras are implemented in eBPF using the basic eBPF primitives. Then we'll move to the Getting Started section, where we'll present how to compile, run, and use PSA eBPF. We'll introduce the PSA eBPF C API and the CLI tool that helps users to manage P4 programs written for eBPF. Moreover, Mateusz will present a hands-on session to give you an idea of how to use PSA eBPF. And we will also show how to integrate PSA eBPF with Mininet. And finally, Jan will show how to troubleshoot PSA eBPF. At the end, I will summarize the tutorial. I will start from presenting the programming guidelines, and then I will conclude giving you an idea of future work that we are planning and how to get involved in the project. Let's start from explaining what actually the PSA eBPF is. In a nutshell, PSA eBPF is an implementation of P4 portable switch architecture for eBPF. The eBPF, as you may already know, is a popular technology for flexible and high-speed packet processing on the Linux operating system. And the open source P4 compiler already implements an eBPF backend, so P4 developers can write P4 programs and compile them to eBPF instructions that are further injected into the Linux kernel to process packets. However, the legacy eBPF backend that is already implemented only supports packet filtering with limited capabilities. Therefore, we came up with PSA eBPF, which is an extension to P4 eBPF, implementing a fully featured portable switch architecture. We believe that the PSA model, as a more feature-rich architecture model, will unleash the full potential of P4 programming for eBPF and will also enable plenty of interesting use cases for end-host networking. The PSA eBPF basically consists of two components. The first one is the PSA eBPF compiler, which sits in the open source P4 compiler repository. The PSA eBPF compiler is responsible for generating the eBPF bytecode that can be further injected to the Linux kernel to process packets. However, loading and managing eBPF programs generated by the PSA eBPF compiler is not straightforward. Therefore, we come up with another component, which is the low-level PSA eBPF C API and the PSA eBPF CTL CLI tool that is built on top of the low-level library. This component hides the underlying complexity and provides an easy tool for P4 users to manage PSA eBPF programs. We'll introduce the PSA eBPF library in the Getting Started section later on. The PSA eBPF workflow follows the standard P4 workflow. A P4 developer writes a P4 program according to the PSA model, and I think it's worth noticing that for PSA eBPF we don't require any custom extensions to PSA programs. Then a developer should use the PSA eBPF compiler to generate eBPF bytecode, which is intended to be injected into the Linux eBPF subsystem and attached to so-called eBPF hooks. However, this process is quite complex, so we provide the PSA eBPF library, as I mentioned before, to simplify this step. With the help of the PSA eBPF API or CLI tool, a P4 developer can load and manage PSA eBPF programs. And once it's done, the attached eBPF programs will handle incoming packets and process them according to the algorithm defined in a P4 program. Now, let me introduce the background information that is necessary to fully understand the design and implementation of PSA eBPF. Basically, eBPF stands for Extended Berkeley Packet Filter, and it provides an in-kernel virtual machine that can safely run eBPF programs inside the Linux kernel. An eBPF program is basically a set of instructions, assembly-like instructions, that are either just-in-time compiled or interpreted. eBPF programs can be injected at runtime, so no kernel extensions or system reboot is required. And there are different BPF concepts that we will be using throughout this presentation, and I will briefly introduce them now. First of all, there is a BPF verifier, which is a static in-kernel checker that verifies if eBPF program is correct and will successfully terminate inside the Linux kernel. BPF verifier makes eBPF programming a little bit more tough because eBPF programmer must satisfy eBPF verifier. In case of PSA eBPF, it is the compiler that guarantees that the P4 program that is compiled down to the eBPF bytecode will pass the BPF verifier. Also, we have BPF maps, which are persistent key value stores that can be implemented, for instance, based on the hash table. And BPF maps are basically a way to share the state between a subsequent eBPF program runs, or between the eBPF program that is running in the kernel space and the user space application that implements the control plane for a eBPF program. There are also BPF helpers, which are external kernel functions that are intended to perform more complex operations. It is because the simple eBPF instructions that are not so powerful. And for instance, to change the packet buffer size, we need to use a BPF helper. Similarly, to make a lookup or update to the BPF map, we also have a dedicated BPF helpers. There is a set of different BPF helpers that the eBPF subsystem provides. Now there is one another eBPF concept, which is a BPF hook. A BPF hook is basically an attachment point for eBPF programs. And Linux provides many BPF hooks. Not all of them are rated to packet processing. In this presentation, we focus on two BPF hooks that are strictly related to the packet processing. The first one is XDP, which stands for Express Data Path, and the second one is TC, which stands for Traffic Control. XDP runs in the NIC driver and provides only the ingress path. Due to the fact that it is implemented at the lowest level in the Linux OS, it provides really high performance. However, it has limited capabilities. For instance, there is no QoS support at the XDP level. Contrary, TC runs before the Linux TCP IP stack, so it's a little bit higher. It's executed a little bit higher than the XDP hook, but it provides both ingress and egress paths. And this hook provides more capabilities. It's more feature rich. For instance, we can integrate TC programs with TCQ disk for QoS, but this comes at the cost of lower performance compared to XDP. Before we go to the design and implementation of PSA eBPF, let me shortly introduce the portable switch architecture that we implement for eBPF. As the specification says, the portable switch architecture is a target architecture that describes common capabilities of network switch devices that can process and forward packets across multiple interface ports. The PSA model consists of two P4 programmable pipelines, ingress and egress, and each of them is composed of parser, control block, and deparser. The packet replication engine is placed between the ingress and egress pipelines and is basically responsible for packet cloning. There is also a buffering and queuing engine that handles packets after they exit the egress pipeline and is responsible for more advanced traffic management, such as scheduling, for instance. The PSA specification also defines a set of basic primitives to operate on packets, such as send or a primitive to send or drop a packet. And it also defines a set of PSA actions that can be used to implement more complex features, such as traffic metering or stateful processing using registers. Finally, the PSA defines a set of packet paths that a P4 program can use for a given network application. So we implement such a packet path like resubmit or packet recirculation. Once I introduce the background, let's move on the design and implementation. In this section, I will give you a complete overview of PSA eBPF. First of all, the main component is the PSA eBPF compiler that translates P4 programs written for PSA to eBPF programs. In fact, the PSA eBPF compiler generates a set of eBPF programs that work together to implement the P4 pipeline. In this tutorial, we will focus on a so-called general-purpose TC-based design that implements any PSA program at the cost of a bit lower performance. By saying TC-based design, I mean that the P4 programmable packet processing is performed in the TC hooks. We have also come up with a more efficient design that offloads the packet processing to the XDP layer. However, we will not cover this design in this tutorial because the design has not been yet merged to the P4EC repository. Nevertheless, there is a clear plan to support XDP-based packet processing, and you can expect it soon. Let's take a high-level look at the TC-based PSA eBPF design. In this slide shows the architectural view on the Linux eBPF subsystem. We show the scenario with two network interface cards, where the one on the left side is the receiving NIC, while the other one is a transmitting NIC. And you can see different, you can see the Linux network subsystem and different eBPF hooks on this diagram. The XDP hook is available on the ingress path, as well as the TC ingress hook. On the egress path, we have the TC egress hook and the TC QDs that handles packets after they are processed by the TC egress hook. And this is how we map the PSA model to eBPF hooks. Starting from the bottom left, we have an eBPF program attached to the XDP hook. We call this program an XDP helper program. In fact, this program does not perform any P4 defined packet processing, and I will provide more details about the purpose of this program in next slides. For now, just keep in mind that the XDP helper program participates in the process of receiving a packet and delivering the packet to the TC ingress hook. The TC ingress hook contains an eBPF program that implements the PSA ingress pipeline and the ingress part of the packet replication engine. In the next slides, I will show how a single pipeline and packet replication engine are implemented internally. A packet leaving the PSA ingress pipeline can be either cloned by using a clone session or multicast group, or just forwarded as a unicast packet. If a packet is cloned, the BPF clone redirect helper is called to create a duplicate of a packet. If this is a unicast packet, the eBPF program will call BPF redirect. In either way, a packet enters the TC egress hook, where the PSA egress program is attached to. There is also an egress part of packet replication engine in the TC egress hook. The packet replication engine is decomposed into ingress and egress parts to realize the clone ingress to egress and clone egress to egress packet paths that are defined by the PSA specification. However, both parts share the same clone session and multicast groups that are represented as BPF maps. Next, a packet leaves the PSA egress pipeline and enters the TC QDs for traffic scheduling or other advanced traffic mechanisms. PSA eBPF implements all packet paths defined in the PSA specification. In this diagram, the red color shows the PSA packet paths, while the green color represents the eBPF implementation. I have already described the basic packet paths, including the NFP path, also the normal unicast, normal multicast, and clone ingress to egress. Packet resubmission can be performed in the ingress pipeline, and it is done by calling an ingress eBPF program in a bounded loop. In the egress pipeline, a packet can be cloned and sent again to the egress pipeline for processing. This is done by the egress part of packet replication engine, and the BPF clone redirect is used for that. The packet recirculation path is done by calling BPF redirect helper to one of the recirculation ports with a special flag, which is called BPF ingress, that says the Linux kernel to start processing from the ingress pipeline. Finally, a user space application can inject packets to the data plane by sending it to the PSA port CPU, which is a special port attached to the PSA eBPF pipeline. Next, I will explain each component participating in the packet processing in more detail, starting from the XDP helper program. First of all, it is a fixed and non-programmable eBPF program attached to a XDP, which processes every packet that is coming to the network interface. The question is, why do we need this program? During the prototyping phase, we encountered a major limitation of some BPF helpers that are available in the TC hook. The limitation is that some of BPF helpers are dependent on the packet type and fail for other Ethernet types than IPv4 or IPv6. For instance, if the TC layer receives an MPLS packet, the packet buffer resizing will fail because the BPF helper does not support packets with Ether type equal to MPLS Ether type. Therefore, TC is protocol dependent. The XDP helper makes the TC layer protocol independent. This workaround works as follows. First, the XDP helper reads an original Ether type and saves it as a so-called XDP to TC metadata. Then the XDP helper program replaces original Ethernet type with IPv4 type and sends XDP to TC metadata in out-of-band fashion, which I will explain in a while. Finally, the TC ingress program receives a packet, reads XDP to TC metadata, and replaces the temporary Ether type in the packet with an original Ether type. In this way, TC layer thinks that it operates on an IPv4 packet, while in fact it can support different packet types. Now, how does XDP helper program send XDP to TC metadata to the TC layer in out-of-band fashion? We support 3 alternative modes for that. The default mode is called meta, and it uses the BPF XDP adjust meta helper to put the original Ether type in a field called data meta. This data meta field is transferred by the Linux kernel from XDP to TC, and this is basically a common way to share state between XDP and the TC layers. However, we have found out that some NIC drivers that do not support this BPF helper. Therefore, as an alternative, we provide a second mode, which is called head, and the head mode prevents a packet with an original Ether type by using BPF XDP adjust head. So in this mode, the original Ether type is carried inside the data packet. Finally, we provide another mode which uses BPF per CPU array map to share the XDP to TC metadata. But we recommend you to use it for testing only, because we may not always have a guarantee that the packet processing in the TC layer will be continued on the same CPU core as the XDP processing. Now, what are the consequences of using XDP helper program? First of all, you will be seeing malformed packets when sniffing interfaces with TCP dump or T-shell. By saying malformed, I mean that the packets will have invalid Ether type. Unfortunately, there is no other way, and we need to live this with this limitation. Additionally, there are some operability issues. For instance, some NIC drivers may not support the native XDP mode, which is required for XDP helper program. Also, the virtual Ethernet pairs require XDP program to be attached to both ends. So if we use this type of virtual interfaces with PSA eBPF, we need to make sure that the dummy XDP program is attached to the second end of a virtual Ethernet pair. In the next slide, I will talk about how a single PSA pipeline is translated to an eBPF program. Each PSA pipeline consists of parser, control block, and deparser, and each of them is translated into a separate piece of eBPF instructions. The eBPF program operates on a packet buffer via the so-called socket buffer packet descriptor, which is a standard way for the Linux applications to operate on packets. The parser is responsible for reading the packet headers. The process is done by translating the parser state machine to a set of sections in the eBPF program that uses load functions to read and save parsed packet headers in the BPF in the per CPU array map. Moreover, our parser implementation supports basic parser primitives such as value set, look ahead, advance, or length. The control block is translated to a set of eBPF instructions implementing the control flow, most likely based on the P4 match action tables. Each P4 table is translated into one or more BPF maps, depending on the match kind, and also one additional BPF array map, which stores a single element, the default action. Moreover, PSA externs are translated to a set of eBPF instructions and BPF maps, and I will explain more details in the next slides. Finally, the deparser takes a parsed packet headers from the per CPU array map and constructs an outgoing packet that is sent out via the output port. As I said before, each P4 table is translated to one or more BPF maps depending on the P4 match kind, and one additional BPF map for default action. In this slide, I will explain what types of maps are generated for different P4 match kinds. Let's start from the exec table. An exec table is a P4 table consisting of exec match kinds only, and in such case, the P4 table is translated to the BPF hash map, and a concatenation of all match fields constitutes a map lookup key. Next, a longest prefix match table is a P4 table with at least one LPM match field and no ternary or range match fields. In such a table is translated to a special BPF map which is called LPM3. This map is dedicated for lookups based on the longest prefix match algorithm. Then we have ternary tables, which are P4 tables with at least one ternary field. For ternary tables, the eBPF subsystem does not provide any built-in mechanisms. Therefore, we decided to adopt the tuple space search algorithm that converts the ternary matching into a set of lookups to BPF hash maps. Finally, PSA eBPF does not support range matching yet, but we do have it on the roadmap. In fact, the range matching can be simply implemented by a naive range to prefix conversion. Now, the PSA specification defines a set of PSA externs, and we implement all of them for PSA eBPF. In the next two slides, I will briefly go through their implementation, and you just keep in mind that in general, most of PSA externs uses a combination of eBPF maps and helpers to achieve its goals. Starting from the action profile, it requires only one additional BPF hash map that stores the mapping between the member ID and action specification. In the data plane code, it results in one additional lookup to this additional BPF map. The action selector is an extension of action profile, except for the map that stores a mapping between member ID and action specification. It also needs two additional maps. The first one is a BPF map, the BPF map of maps that stores action selector groups and their members. and the second one stores an action for an empty group. In the data plane, action selector requires a sequence of BPF lookups to different maps and a set of instructions to calculate hash from selector fields to dynamically find a member from the action selector group. The counter extern is implemented as a BPF array map, and the PSA eBPF compiler generates a separate instance of BPF array map for each counter instance. In the data plane, the counter is updated by calling the sync fetch at function that guarantees the atomicity of the operations. The direct counter does not require any additional BPF map. Instead, the direct counter state is kept inside the BPF map that implements a P4 table. In the data plane, the similar method is used to update the direct counter state. The digest extern uses a BPF queue map for each instance of digest. The BPF queue map implements a FIFO queue, and the data plane uses the BPF map push element helper to insert data into a queue. Then the user space is responsible for performing periodic queries to get the next piece of data from the data plane. Moving on, we also implement meter. Each meter instance is translated to a BPF hash map that keeps the internal meter state. This map also uses BPF spin log that provides concurrency management in the multi-core CPU environment. In the data plane, eBPF program retrieves a current timestamp that is required for metering algorithm by using a dedicated helper for that. Moreover, eBPF program must perform a single lookup to get a current meter state and a single update to modify the internal meter state. Direct meter works similarly, but it does not require an additional BPF map. Instead, the BPF map representing a P4 table is extended with a BPF spin log for concurrency management. Also, the eBPF program does not need to perform a lookup because the internal meter state is retrieved when a lookup to a P4 table is done. However, the meter state modification is still required. Next, we implement registers for stateful processing. Registers use either BPF map or BPF hash map, depending on the width type of index. Then the eBPF programs perform a lookup to a map for register read operation and update to a map for register write operation. There are other externs like hash checksum and internet checksum that do not require any additional BPF map. The PSA eBPF compiler generates the set of eBPF instructions to calculate hash or checksum values from a given data. Finally, the random extern uses a BPF helper that returns a pseudo-random number. Next, let me explain how the packet replication engine is implemented internally. As you already know, the packet replication engine is split into the ingress and egress parts and integrated into eBPF programs for ingress and egress respectively. Both clone sessions and multicast groups are organized as BPF map of maps, as you can see in the diagram. The diagram shows the memory organization. The outer BPF map is an array map that stores the mapping between clone session ID or multicast group ID, and the inner BPF map that stores members of either clone session or multicast group. The inner BPF map stores members that include all necessary information to perform packet cloning. The entries are organized as a linked list abstraction that enables more efficient iteration over the entries from within an eBPF program. In the data plane, eBPF program firstly performs a lookup to an outer BPF map to get an inner map based on either clone session ID or multicast group. And then the eBPF program iterates over the inner BPF map and calls BPF clone redirect helper for each member. This method enables linear complexity when performing packet cloning, and the complexity depends on the actual number of members configured. Finally, I will show how we map the buffering and queuing engine to the eBPF subsystem. In fact, the PSA eBPF leverages TCQDisk to map this functionality. The TCQ disk is a powerful QoS engine that is provided by the Linux kernel, and it gives a way to perform traffic shaping, scheduling, policing, or dropping, depending on the TCQ disk configuration. A user can configure classful disciplines such as HQoS or a number of classless disciplines. Therefore, the TCQ disk provides a full spectrum of different QoS policies that a P4 developer can use and apply to the packets processed by the PSA eBPF programs. eBPF programs generated by the PSA eBPF compiler interface with TCQ disk by a means of PSA class of service metadata. This metadata can be set inside a P4 program, and the PSA eBPF compiler sets the SKB priority field based on the class of service field. Then the priority field is passed to the TCQ disk to determine a QoS class based on pre-configured mappings. Let's move to the Getting Started section, where we will show PSA eBPF in action. Firstly, you need to know how to compile P4 program written according to the PSA model to eBPF bytecode. For that, you need to follow the two-step approach. Firstly, the P4 program is translated by the PSA eBPF compiler to a set of C programs. The C programs have a clear predefined structure that we'll explain in more detail on the next slide. But then you need to use CLang to compile these C programs to eBPF bytecode that can be injected into the kernel. On this slide, we provide the commands reference, so we can use P4C eBPF, then CLang and LLC to generate the target eBPF bytecode. But we automate this process by providing the makefile, which is a part of the P4C repository. Now let me explain the structure of the C program generated by the eBPF compiler. The first section on the top is a preamble, and it contains basic includes, helper functions, and type definitions that are used throughout different eBPF programs. Then we have the section that defines size and types of different eBPF maps that implement P4 tables, PSA externs, or packet replication engine. Then we have 4 eBPF programs. The first program, which is called map initialize, is in fact it's not a program that is intended to do a packet processing. This program is responsible for initializing the default actions, consent trace, and all different constant variables for the PSA eBPF programs. And it is called only once. We'll explain more details about this process on the next slides. Then we have the XDP helper section that implements eBPF program that implements the XDP helper which I introduced in the design section. Then we have 2 sections that implements P4 programmable packet processing. The TC ingress is generated from the PSA ingress pipeline and contains the ingress part of the packet replication engine. The TC egress includes the PSA egress pipeline and the egress part of the packet replication engine. Now Jan will take over the presentation and say a few words about PSA eBPF API and the CLI tool.
Once a P4 program is compiled, you should use the PSA BPF library or a PSA BPF CTL tool to load and manage eBPF programs. In this slide, I will give a quick overview of PSA BPF. First of all, PSA BPF is a repository which has 2 components, a low-level library called PSA BPF and a PSA BPF CTL, which is a command line tool. PSA BPF is designed to manage PSA eBPF programs in almost every aspect at the level of runtime. It allows to load and unload compiled programs to or from eBPF subsystem, attach and detach programs to or from an interface to behave as a part of PSA switch or a normal interface. PSA BPF allows for table management, for example add and delete table entries, and manage externs. Allows also to configure packet replication engine. Let's look at the library. It exposes C API, of which example for digest we have in the frame. Internally, libbpf is used to manipulate eBPF subsystem, but PSA BPF tries to hide dependency on libbpf and its API. Upper layer doesn't need to know about libbpf and other eBPF stuff, only the PSA primitives and API from PSA BPF. Library doesn't use P4Info. Instead, it uses BTF, generated by C compiler, so there is no need for additional steps. BTF allows to deal with memory layout, so upper layer can operate only on plain values for given fields. Side effect is that library can't obtain relation between P4 objects. For example, which table use which implementation. These things have to be done in the upper layer using P4Info. Now let's talk more about PSA BPFCTL, a command line tool. As I said in the previous slide, it's a part of PSA BPF repository. The tool uses C API from PSA BPF library for interaction with BPF subsystem. It doesn't implement nav features in this area. It only parses command line arguments, calls required C API from PSA BPF, and prints results in JSON format if applicable. Support for all the externs is not implemented yet. For now, PSA BPF and PSA BPFCTL supports pipeline management, add or remove ports, clone sessions, multicast groups, table management, operation on extents, action selector, meter, digest, and counter. PSA BPF, both library and CLI tool, are still under development, so other externs will be also supported, but changes to CAPI and or CLI and or output data in JSON are still possible. In this slide, I will explain one of the most important PSA BPFCTL command: how to add an entry to a table without implementation. In the top right corner, there is a sample before table. Table has three keys: exact, LPM, and ternary. It also specifies three possible actions: Act A, Act B, and no action. This is the place where we can determine the action ID of an action. No action always had ID 0, no matter where it is placed in the list. Other actions has IDs starting from 1 in the order of appearance in the list. In this example, Act A has ID 1 and Act B has ID 2. Below the P4 table is a sample PSA BPFCTL command, which adds a new entry to a such table. First, we have sentence PSA BPFCTL table add, which causes setup new entry. Next, there is a pipeline ID. After it is fully qualified table name. Next, it is an action ID. As I said, action ID 2 denotes action Act B. After that, there is a key keyword and set of three keys. Exact match key is just a value. LPM key uses to separate value and prefix length. Ternary key require value and mask. They are separated by the caret character. Table with ternary key require priority, which is denoted by keyword priority and followed by value at the end of this command. Keyword data denotes the end of key specification and starts arguments for the action. In this example, there is only one parameter for action, but there might be more by typing next values. It's worth to note that you can use IPv4 or MAC address as a value for key or action data. IPv6 is not supported yet. Numbers can be specified in binary, octadecimal, or hexadecimal format. In this slide, I will explain details of how to load and initialize PSA eBPF programs. First of all, compiled programs must be loaded into kernel and pass verification by in-kernel verifier. It may occur that some programs fail this step due to, for example, too many instructions in the program. The next step is to pin eBPF objects under pipeline directory in the BPF file system. This allows to have multiple independent pipelines, each with own programs and maps. Maps are pinned under maps subdirectory. The last step is to initialize maps by running map initializer. It is a separate program which initializes maps with default values, for example, default actions, const entries, etc. This program should be called only once, just after loading all the PSA eBPF programs. All the mentioned steps are done by a single invocation of PSA BPFCTL command. To execute it, you need only pass the pipeline ID, it is n in the example command, and file with compiled PSA eBPF programs. When PSA eBPF programs are loaded into eBPF subsystem, they do not process packets unless they are attached to one or more interfaces. There are three PSA eBPF programs to attach to an interface: ingress pipeline, egress pipeline, and XDP helper. Linux TC requires to create QDisk to be able to attach BPF programs, so new one is created during attaching an interface. When an interface is detached, created TC QDisk is removed with the PSA eBPF programs, and the XDP helper is detached from interface. All of the PSA eBPF programs are not removed from eBPF subsystem when an interface is detached. There are two PSA BPFCTL commands to manage ports, one for attach an interface and one for detach an interface. In both commands, you must specify the pipeline ID and name of the interface.
On hands-on session, we would like to show you three scenarios to make you familiar with the compilation process and the PSA BPF CTL tool. Our demo topology consists of four Linux network spaces: client, switch, server 1 and server 2. All of the steps that will be presented there are published on PSA eBPF demo GitHub repository. And these three scenarios, load balancer, rate limiter, and QoS, are implemented in the same demo.p4 program. To compile it down to eBPF bytecode, we need three steps. First step is to compile down demo p4 to C representation using our P4C eBPF compiler. Please remember to use arc PSA option. Next, from C-like code, we compile it down to eBPF bytecode. This is two-step compilation. Calang produces intermediate representation, and from this, LLC generates eBPF bytecode. Why? The Linux kernel supports different eBPF instruction sets. We can select concrete instruction set using MCPO option. Once we have compiled program to eBPF bytecode, we can load it to the eBPF subsystem and attach to ports. To load programs, we use PSA BPF CTL pipeline load command. To attach ports, we use pipeline add port command. First scenario, load balancer, performs load balancing HTTP requests between two HTTP servers running on server 1 and server 2. It uses action selector with a group of two members that have a data to forward traffic to either server 1 or server 2. Second scenario, rate limiter, performs rate limiting on specific port. In that case, traffic forwarded on first port is limited to 1 megabit per second. Last scenario shows traffic prioritization. We use class of service field from PSA metadata to determine QoS class in TCQ disk. In that scenario, ICMP traffic receives higher priority. From the beginning, let's explain briefly a demo P4 program. This program has two important tables, table routing and table QoS classifier. Table routing is used to forward packets and has action selector on few fields. By this action selector, a load balancer scenario is realized. QoS scenario uses QoS classifier table, where based on IPv4 protocol field, set priority action sets class of service. And rate limiter scenario based on method instance, which is executed in forwarding action, and as an index, a port number is used. Okay, let's go to the load balancer scenario. Firstly, let's deploy a topology. After that, I will compile a demo program, first from P4 to C, then from C to eBPF bytecode. As a next step, I will load a program and attach it to ports. Program has been loaded and attached to ports. Last thing that is common in all scenarios is basic forwarding and RP table entries. And this script installs these entries. So let's run this. Okay, now we have deployed and configured topology. Let's show you entries that are relevant to this load balancing scenario. First two commands add members that have action data to forward packets to server 1 and server 2. Next, we create a group and add these members to that group. Last action selector member has a data that forwards traffic from servers to client, so in opposite way. At the end, table add command associates action selector members with routing table. Okay, so now let's run this scenario. Okay, last thing is install action selector rules, and as you can see, HTTP requests are load balanced more or less equally. Okay, I'm stopping this scenario and we are going to the next one. The next one, which is a rate limiter. In this scenario, we have to install only one rule that configures a meter. PSA BPF CTL meter update command has three arguments. Index specifies output port after there is a pair of peak information rates, bytes per second, and peak packet size in bytes. After that, second pair of committed information rate in bytes and committed bucket size in bytes. Now I'm starting a traffic between client and server. As you can see, there is 100 megabits per second bandwidth, and our rate limiter will limit this link to 1 megabits per second. You can see the speed decreased to 1 megabit per second. Let's stop this and go to the last scenario. Traffic prioritization scenario requires a pre-configured PCQ disk. So let's configure this Linux TC subsystem. And this command creates per each interface different classes of service that can be chosen by our running before program. Next, let's start a ping between client and server 1. The next step, I will create a congestion on this link so that there will appear longer delays. You can now observe a delay that has more than 300 milliseconds. Of course, it will change when we set higher priority for ICMP traffic. So let's do this. Thanks this simple command. This command just inserts an entry that selects set priority action on ICMP packets. As you can see, delays for ICMP traffic has decreased. Okay, that's all for this session. Thank you very much.
Mateusz just showed how to manually compile and configure PSA eBPF. However, we also provide the minute support so that some steps can be automated. and you could test more advanced topologies on your laptop. We have prepared a basic Minet wrapper on top of PSA BPF CTL that allows us to integrate PSA BPF with Minet. I will now show a quick demo of using PSA BPF with Minet, but you can also find the demo scripts in the PSA BPF repository. For the demo, I will use a very simple P4 program that is called simpleswitch.p4. This program is basically doing very simple layer 2 forwarding based on the destination MAC address. The demo topology that I will be using is composed of a single switch and two hosts. So let me show this topology first. So as you can see, we create a switch, a single switch, and we pass BPF path that defines the path to the eBPF bytecode that is generated by the PSA eBPF compiler. We also add two hosts, and then in the main function we create the Minet topology. Note that we use the PSA eBPF switch object for the P4 for the Minet switch. Also, this script installs two table entries to the PSA eBPF switch. And these entries are responsible for forwarding packets between host 1 and host 2. So let me first compile the demo program. And once it's compiled, we can start the Minet topology. So we can see that the Minet topology is up and running. We can now check the table entries that are installed inside the switch. And you can see that for the MAC address of host 2, we forward packets to the port number 12. And for the host 1, we forward the packets to the port number 11. Now I can check a basic connectivity using the ping command. And you can see that the basic connectivity works. And this is how we can use Minet with PSA eBPF. Back to Jan, who will show how to troubleshoot PSA eBPF.
In this slide, I will show you a few methods how to troubleshoot PSA eBPF programs when something doesn't work. The most important is the trace flag for the P4C eBPF compiler. When used, PSA eBPF programs will log what they are doing during packet processing. They would print actual parser states, extracted values into headers, executed actions and externs, used keys for tables, and more. There are two ways to read these logs. Use command bpf toolproc tracelog or cut one of the system file. Analysis of the logs allows to debug P4 programs. bpf tool is a command line tool that can be widely used to troubleshoot PSA eBPF programs. It is part of the Linux source code. It allows to list loaded eBPF programs, show interfaces with attached eBPF programs, can show maps and inspects its values, even modify them. Sometimes it is useful to analyze eBPF bytecode to understand the exact behavior of the program. When you no longer need the PSA eBPF programs, you should completely remove them from eBPF subsystem. To do this, all the added ports have to be detached and then programs can be unloaded from the eBPF subsystem. As a result, there shouldn't be loaded programs maps and files in the BPF file system related to given pipeline. Sometimes there is need to completely wipe state of the eBPF subsystem. One way is similar to removal of PSA eBPF programs. Just remove all the PNS objects and detach every interface. A more reliable method is to reboot your operating system.
It's time to summarize the tutorial now. Let's start from the programming guidelines. If you write a PSA program from scratch for the eBPF backend, it's worth to follow these programming guidelines to maximize the performance of generated eBPF bytecode. First of all, try avoiding egress processing. If the PSA egress pipeline is empty, the PSA eBPF compiler will optimize the eBPF egress program out, and this, according to our benchmarking, will result in a noticeable performance gain. Also, each P4 table lookup contributes additional processing overhead. So try to minimize P4 table lookups. For instance, you can guard P4 table lookups by header of validity, or you can exit pipeline earlier if you don't need further processing. So this might be a little bit tricky, but we believe that this is possible to minimize P4 table lookups in certain scenarios. Other than that, use index type that is equal or shorter than bit 32 for PSA exters. In such a case, PSA BPF compiler will use a more efficient BPF array map with instead of BPF hash map for counters, registers, and meters, and this will also result in a noticeable performance gain. And finally, if possible, prefer direct exters over indirect exters. The indirect counter and meter require additional lookup to eBPF map. So using direct exters reduces the processing overhead and might make your programs more efficient. To sum up, we truly believe that PSA eBPF brings the power of P4 and PSA to Linux and eBPF, and it enables programming of advanced use cases for end-host networking with P4. The advanced use cases that we have in mind is, for instance, P4 programmable Kubernetes plugin, ideally with the host INT support. Another interesting use case is a software-based P4 implementation of P5G UPF. And we also think that with our solution, we could, as a community, we could implement the P4 programmable data path for BERT or other routing daemons that can be really high performance. As a future work, we plan to integrate PSA eBPF with a P4 runtime software stack so that we can integrate with remote SDN controllers. There are also some missing features like range matching, which we like to work on. And finally, there are some enhancements of eBPF subsystem itself in the latest Linux kernel version. Therefore, we would like to meet the parity so that the generated eBPF programs can be more efficient or more scalable. Finally, we are eager to support you in using PSA eBPF in your projects, and we would like you to give the PSA eBPF a try. PSA eBPF documentation in the open source P4 compiler repository is a good starting point. Also, feel free to reach out to us and open GitHub issues to report a bug or ask you questions. You can also contact us on the P4 eBPF channel in the P4 Lang Slack. And if you want to learn more about eBPF, we recommend you the eBPF XDP reference guide from eBPF.io. I truly believe and I hope that you benefit from this tutorial, and thank you for your attention.